right, so we're now going to dive into our next concept. This is C10, and this is for chapter 11. Chapter 11, we're going to dive into AC power. And actually, just like before, and just like what we've been doing before, you may notice that. Let me just show you really quickly. In part one of the class or the textbook, we looked at DC circuits. And we did look at power. Let's see if I can pull it up somewhere. Let's see. Yeah, see power right here. So we're looking at chapter one. So this is way back then. And we were reminded that power is equal to your current times your voltage. And just like how you have these equations where there's a time varying, there's instantaneous power for DC circuits. Well, guess what? For AC circuits, you have something similar. You have instantaneous power, but there are also other powers that exist as well. We'll talk about those in other videos. But in this case, for instantaneous power, this is the most simple one. The direct connection, the first level of in terms of just understanding power. This is the first thing is that, well, power here is going to be the same thing. It's going to be power is equal to voltage times your current. And one thing that we note here is that your voltage and your current, they're not just single digit volts and amps numbers, but obviously in AC, there is some sort of signal or that is somewhat time varying. So what is instantaneous power? Instantaneous power is the power consumed at any instant in time, and it's also the rate. So as you remember, the power from chapter one, we did have a differential actually attached to it. So as a quick reminder here, power is equal to dw over dt, and that itself, if you were to you make the connections, it's equal to your voltage times your current here. So for here, we're just looking at the AC version. Again, it's the same concept, so V times I. And if you go ahead and actually multiply them together, and I'm not necessarily going to do show you the work here, but you can go ahead and check the textbook and you can kind of see it laid out step by step. But your power here, with respect to time, you end up yielding this equation here. So we did box it because there's something very unique about it. And obviously, this is the expanded view. Could you have grouped up 1/2 V max current max? Yes, you could. But I do want to separate it just so we can see a couple things. First off, you notice that only one of the terms has actually the time variable in it, and that's actually this side of it. And then the other side is actually more of it actually doesn't have the time variable. So that's one thing you want to note, is that one is constant or it's time independent, which is going to be this side. And it's really just dependent on the phase difference. The second part has some sort of frequency to it. There is, it is actually time varying in this case. So just a couple things to note here. So for the, how does this all kind of wrap together? Well, when you're given a sinusoidal wave, or in this case, let's say cosine or something. Let's say if you had a normal cosine graph. So I know I'm using this version here that you see on my notes page, but you see where the dotted line, how that's the center of the wave. Well, normally when we first were introduced to sine and cosine waves, this dotted line started here at the x-axis here at y equals 0. Well, in this case, in this graph, power equals 0. So that's how we were introduced to it. Now, if we wanted to, let's say, increase that or something, or move it along up on the x-axis, you would actually modify this portion of the equation so that now the base or the starting or the middle of the wave is actually now increased a little bit more. So this is mathematically characterized by these middle terms here, the phase angle, so the phase of the voltage minus the phase of the current. So as the phase goes from 0 to 90 degrees, cosine of 0, as you know, is going to be 1, and cosine of 90 degrees is going to be 0. So at cosine 90 degrees at 0, this dotted line is going to come to the bottom on the axis here. But then as you, let's say, increase this to cosine 0, which is going to give you 1, it's going to be equal to 1/2 VMIM. So again, this is 1/2 of the max voltage times the max current. And then that's going to give you this here. So now this graph depicts something that's going on here. Obviously, we didn't give any numbers here, but it depicts something is happening, or some sort of shift is happening with this wave. Now, obviously, sinusoidal waves have both a positive and negative component to it, but then later on, we'll see later when it comes to like the average, eventually you won't necessarily get negative power, but you'll usually get some sort of average positive value here. So maybe it might dip it down for a little bit in the negative, but eventually what this term really does, when you actually have something, when you have a constant here, it actually allows your signal to be quote unquote more positive, or there's more at any given time. Your signal is in the positive range, not so much in the negative range here.